a positive error. A lot of people just say it's due to experimental error, but pretty soon, that starts losing its meaning unless you start really analyzing it. What specifically was it about this experiment? But, there's a lot of places for error in this particular experiment.
But for this experiment, we don't have to explain what we think might be.
Yeah, one thing you could have done is if you look at the graph, you're just changing the slope of the graph just a little bit, how much error does that yield? And so what you do is you do a maximum fit and a minimum fit to see what the range is. And then from there you can see is it within the range of the error. We didn't do a full error analysis of this particular experiment, right? You just do the numbers, but you'll get the full error analysis later as you go on. And so, yeah, for now it's okay, don't worry about it. All right, so today we're going to continue. Were there any other questions? Chapter 12 and 13.
Oh, I have another question. Just to, for the conjugate base.
Go ahead.
For the conjugate base, the less charge it has, the less negative charge it has, makes it more stable, right?
Yeah.
So therefore, it's
less reactive. No.
Wait, the weaker the base.
What are you talking about? The acid? It's conjugate acid?
The conjugate.
Yeah. Yeah. The more stable the base is, the more reactive it's.
It's conjugate acid.
Yeah. It's conjugate acid.
So the weaker the base, the stronger the acid.
You're right.
The conjugate.
Right. It's a conjugate relationship.
Yeah.
The stronger the acid, the weaker the base. The weaker the acid, the stronger the base. It doesn't want to lose its proton. There are other factors that you have to consider. The three factors. Well, let's take a look at chapter 12 and 13, solids, liquids, and solutions. And so, chapter 12 starts off with intermolecular forces, IMFs. And so let's just continue here. The IMFs, IMFs sometimes are called van der Waals forces. Where have you heard van der Waals before?
The equation.
Yeah, the van der Waals equation. What was the van der Waals equation all about?
It was non-ideal gas.
Yeah, non-ideal. What causes gases to deviate from ideal behavior? Excuse me.
They have volume.
They have volume and
The particle.
IMFs, right. So van der Waals studied these IMFs. That's why we have the correction A in van der Waals equation for IMFs. And so let's take a look at the IMFs. London, or dispersion forces. How these operate is we have an instantaneous dipole. Induced dipole. Arrangement. Helium is about the most ideal or about the least ideal gas you can have?
Most
Helium is about the most ideal gas you can have because, one, the size is very small, plus two, the intermolecular forces are very weak. And so if we think about helium, here's another helium. Are these two heliums going to be attracted to each other? No. They shouldn't be. The attraction is going to be based on what type of attraction do we see in chemistry? Electrical. And so if you look at the electron cloud here, electron cloud is pretty uniform like this. There should be no net attraction, but it turns out that in one instant of time, are you guys already familiar with this? Of how dispersion forces work? No? All right. In one instant of time, the electron cloud might be polarized. Polarized, that is, both electrons, let's say, are on the left side. And so this is called an instantaneous dipole, because the instantaneous dipole, we can see that the negative charge is on the left and the positive charge is on the right. This instantaneous dipole doesn't last for very long. It's just one moment of time. What that's going to do is it's going to induce a dipole in the other. And so this adjacent helium is going to see the positive charge region, and the electron is going to migrate towards there. That's going to induce a dipole over here. And so we call this an instantaneous induced dipole. The first one.
What causes the instantaneous?
I'm sorry?
What causes it?
What causes it? The random movement of the electron cloud density. And so both electrons here, the instantaneous dipole induced. Time average, though, there's no dipole. We call helium nonpolar. It's nonpolar, so there shouldn't be any attraction, electrical attraction, between the two. So we got instantaneous induced dipole. Helium, I mean, this is weak. You know, what's the boiling point of helium? The boiling point, or the 4 Kelvin. In other words, you have to cool helium down to 4 Kelvin in order for it to condense into a liquid. It'll condense into a liquid once the attraction gets strong enough to hold the helium atoms together. You know, something has to hold the helium atoms together, and it's not going to be their weight. So, a boiling point is 4 Kelvin, whereas something like xenon has a boiling point lower or higher than helium. So let's look at xenon. Xenon has 54 protons in the nucleus, and how many electrons? 54 electrons. And so what happens is, in one instant of time, you know, we might not have 2 electrons, we might have a lot of electrons on one side, right? So let's say most of the 54 electrons move to this side, we're going to set up a huge instantaneous dipole, right? And so that's going to induce a dipole in an adjacent xenon. And so for xenon, what do you expect, the attraction to be stronger or weaker than helium? Well, yeah, much stronger. And so the boiling point is much, much higher than 4 Kelvin. And so this is going to have much stronger IMFs, dispersion forces. So basically, the magnitude of the dispersion forces depends on the number of electrons. So the strength depends on 2 things. One, the number of electrons. You know, the greater the number of electrons, right, the more polarizable the electron cloud. Polarizable just means it can be distorted. The stronger the dispersion forces. The second thing it depends on is surface area. You know, if you have a molecule like this, let's say versus a molecule like this, let's say both of these have the same number of electrons. Which one will have a stronger dispersion force? It turns out that this one will have a higher boiling point because of the surface contact. And so dispersion forces occur in all molecules. Anything with electrons.
Can you explain again what the drawing is? What are you trying to?
The drawing is a molecule, molecular shape. So So you have a molecule that's kind of spherical, actually it's spherical, versus a molecule that's straight chain. These both have the same number of electrons. They're both the same formula. These are called isomers. Yeah. Isomers. Isomers is the same formula, different structure. Which one's going to have a higher boiling point? You don't need to know the names of these. This is neopentane, this is pentane. Which one's going to have a higher boiling point? The one on the right. And so the boiling point of this is higher than the boiling point of this. Why? Because more surface contact.
I didn't know it was higher.
Because the boiling point depends on the strength of intermolecular forces. The stronger the intermolecular force, the higher the boiling point. Because boiling, what you have to do is you have to break apart two molecules held together in the liquid state. And so the stronger the two molecules are held together, the harder it is to break them apart. And so the higher the boiling point.
The more surface you get, then happens in more high. The more surface you get, then happens in more higher.
Yes, the more surface contact between the molecules,
How do you work?
the more surface contact between the molecules, the higher the boiling point, because there could be more interaction between molecules like this. So the sphere, which is a tetrahedral, has a minimum surface area. Spheres have the minimum surface area per volume, so the amount of contact they do is not as great as something like this. This would be more like a noodle structure. You know? And so there's going to be more surface contact.
So there's a high boiling point because of the surface area, right? There's more contact between them.
Yes.
There's more contact between.
The more interaction you have, right? The more interaction you have, the stronger the force is going to be.
Is it between atoms?
No, it's between the molecules, yeah. Uh-huh.
When you're talking about strength, what do you mean, like, strength and what?
Strength,
Yeah.
intermolecular force, electrical attraction. It's like in one instant, for example, here, which one do you expect to have the higher attraction? Between two molecules like this? Or two molecules like this? Yes, because this is Coulomb's law. Can somebody remind me of Coulomb's law? You know, this is from week number 1. Has anybody reviewed anything?
Coulomb's law.
Somebody remind me Coulomb's law.
Electric attraction.
I mean, I expect by the end of the semester, you must have read Coulomb's law like 50 times by now, because repetition, right? Although maybe not.
KQQ R squared. I just don't remember.
Well, no, you don't need to know the formula. You just need to know the strength of the attraction depends on charge and size. Charge and size, right? And so we're always looking for, you know, if it's a bigger charge, the strength of the attraction is going to be bigger. The reason Coulomb's law is so important is, what is chemistry all about? Electrical forces. And if you don't know Coulomb's law, what are you doing about, chemistry? It's all electrical attractions, like, covalent bonds, ionic bonds, and intermolecular forces. Intermolecular forces are just electrical attractions. That's all they are. Except the electrical attractions aren't so strong. The strongest intermolecular force is about 25 kilojoules per mole. It's called a hydrogen bond. What is a covalent bond running? What's about the weakest covalent bond? The weakest covalent bond is around 100 kilojoules per mole. Right? And so we call these IMFs because these aren't strong enough to be like a covalent or ionic bond. And so these are much weaker. In fact, these dispersion are incredibly weak for small molecules. As the molecules grow bigger, the dispersion forces get quite a bit stronger. And so for very large molecules, the dispersion forces are extremely strong. And so,
But you said we call them IMS because they aren't strong, you know, like as strong as
regular bonds. And so, dispersion forces are big for big molecules. Like wax. Wax is just a hydrocarbon, these very, very long hydrocarbons like this. You just got to keep adding more carbons, so they're extremely long chain hydrocarbons. In wax, you know, compared to something like pentane, pentane's liquid, wax is actually a solid. And so if it's a solid, that means the intermolecular forces holding the wax molecules must be quite strong. Asphalt. Asphalt is a mixture of hydrocarbons, like crude oil. You know, and you have these big molecules. Is the street going to vaporize away? You know, the street you're driving on? No, because the dispersion forces holding those non-polar hydrocarbon molecules must be very strong, right? This is solid. And so these are strong, fairly strong. But for small molecules like helium, it's not so significant. Kind of weak. Dispersion forces occur in all matter. So let's write that down. I have to put a little qualifier on in all matter. With electrons, of course. It has to have electrons, otherwise you can't polarize the electron cloud. It's got to be electrons. And so when somebody asks you, you know, what are the intermolecular forces, you know, one for sure is going to be dispersion or London forces. Everything has it. But there could be other forces present as well. And so the next type of force is called dipole. And here we need a permanent dipole, not an instantaneous.
Is that what those?
That's the second molecular force.
Yeah. There are only three.
It's a force, right?
Yes. IMF, dipole. So if we look at HCl, HCl has a permanent dipole moment. Looks like this. That means this part is negative, this part is positive. And so between two HCl molecules, we're going to have two types of forces. What types of forces hold two HCl molecules together? One is dispersion and the other is dipole. And the dipole force is, you know, this is permanently polarized like this. And so how do the dispersion forces work? Well, the dispersion forces work like this. So these are the permanent dipoles here. But, you know, these permanent dipoles are time average. The dispersion forces work like this. You know, the dispersion is once in a while the electrons are going to be quite polarized. And so they could be polarized like this. So for example, let's say more electrons migrate to chlorine. Or like this, you know, more electrons migrate to hydrogen and decrease. And so what we see is in instance of time, you know, the dipole moment's actually fluctuating. You know, bigger, smaller, right? Because the electrons aren't static. Over time, we can average it to these permanent dipoles. But in one instant of time, take a look at this dipole. It's quite big, right? And so if it's quite big, then what we're going to have is we're going to have dipole and dispersion. Forces attracting them. So what do you think is a stronger force, dipole or dispersion? Dipole is, it's a permanent dipole versus an instantaneous dipole. So for small molecules, dipole is stronger than dispersion. A temporary dipole versus a permanent dipole. Both of them rely on dipole. All right. The next force is the H bond. This is number 3. The H bond is thought to be the strongest of these all. And what the H bond is, it's an unusually big dipole.
Quick question. There's a big molecule. How does it work for the chain?
Big molecules, dispersion dominant. Okay, but if you have hydrogen bonding, that helps as well. But typically, it depends on how much. So unusually big dipole. When we have oxygen bonded to a hydrogen, then oxygen is quite a bit more electronegative. And so when we look at the electron cloud here, the electron cloud is highly polarized. Towards hydrogen, or not toward hydrogen, towards oxygen. If the electron cloud gets polarized like this, then what we have is we have a partially exposed proton. A partially exposed proton because the electron cloud isn't shielding it. And so what that means is we get an unusually big delta plus. This delta plus is unusually big, almost a full charge. Almost a full positive charge. And so this partially exposed proton can occur for oxygen-hydrogen bonds, fluorine-hydrogen bonds, and nitrogen-hydrogen bonds. You get very large delta pluses. So what this means is that we got unusually strong dipole-dipole interactions, attractions. So unusually strong dipole attractions. This is H bonding. And so H bonds are thought of as the strongest. This is about 25 kilojoules per mole, about a quarter of the weakest covalent bond to break, followed by dipole, followed by dispersion. This is for small molecules. This is review, right? Is this review? Yeah. Everybody should have had these in Chem 4, correct?
There's a big molecule in splits. H bond is still the biggest one.
Well, big molecules complicate things. And so let's take a look at some trends here. Okay. Actually, let me show you the figure in our book here. Or maybe. So what we do is we put the molar mass down here, and then we put the boiling point here. And we look at how the boiling point changes. And so molar mass is going to be proportional to the number of electrons, right? Molar mass is proportional to the number of electrons. And so you can see here, as the molar mass increases, what do you expect to happen to the boiling point? It increases.
That's for big molecule.
No, this is just for, the bigger the molecule, the higher the boiling point, regardless. Now, what we'll do is we'll look at polarity, too, actually. Let me bring up the figure here from our book. If we, to make a fair comparison, we should compare things of equal molar mass. And then if we add a dipole in an interaction, the boiling point should increase, because not only do we have dispersion, and so this would be something that's nonpolar, but we have increasing polarity here, or increasing, I shouldn't say polarity, dipole here. So this is the basic trend here that we'll see in this chart. So what this chart is showing is just showing increasing molecular mass as we go left to right, so stronger dispersion forces, electron cloud more polarizable. And then for items of similar molar mass, we're looking at increasing polarity. And so let's ignore HI for right now. We'll go with tin. Tin tetrahydride, this is nonpolar. And then we go to antimony trihydride, which is a trigonal pyramidal structure, and that's polar. And then we go to hydrogen telluride, which is going to be the most polar. Tellurium is the most electronegative. Tellurium, antimony, and tin. Okay, the same thing here. Germanium, tetrahydride, fewer electrons, and then we increase the polarity here. So arsenic, which is going to be trigonal pyramidal, and hydrogen selenide, all these have the same number of electrons. Difference is, selenium is the most electronegative, so it's going to be the most polar. So this is going to have the strongest dipole. And so if we have dispersion here, and then we add the dipole, the strength increases. And that's a general trend for all these. Now, this is going to be a little unusual because here, methane, polar or non-polar? Non-polar. Methane and ammonia have the same number of electrons, but the difference is ammonia is a lot more polar, right? And ammonia is unusually polar because of its partially exposed proton, which causes hydrogen bonding to occur. And so normally the dipole trend is like this, the more polar it gets, stronger. But here it's unusually big. Do you see that? For the hydrogen oxygen, the hydrogen fluorine, and the hydrogen nitrogen bond. And so this you don't have to know accurately. You just know that as the mass goes up, this is the mass, what happens to the boiling point? It goes higher due to dispersion. Then we look for additional forces in there. Dipole interactions. Dipole interactions can help strengthen that. Now, it's hard to make comparisons. Like for example, tin tetrahydride is non-polar, but HCl is highly polar. And so if somebody asks you, what has a higher boiling point, HCl or tin tetrahydride? Tin tetrahydride only has dispersion, HCl has dispersion and dipole. Well, tin tetrahydride, which means what wins? Eventually, size matters, right? Now, if you have a lot of hydrogen bonding interactions, that can change things as far as the ordering goes. But it appears like HCl. Which one's more polar, HCl or HI? No. HCl is more polar, so HCl is going to have stronger dipole. So HCl has stronger dipole, but which one has a higher boiling point? HI because size matters, right? HI is bigger. That means electron cloud is much more polarizable. So, as far as like looking at HCl versus HI, how could that be? Because if you look at HCl's got a much bigger dipole moment. Much bigger than HI. HI is very small compared to HCl. And so how could HI have stronger attractions? All right, how can it have stronger attractions? Because the electron cloud can become polarized. And so in one instant of time, the dipole, because this has so many electrons, the dipole moment can grow huge. Right? Whereas this has a lot fewer electrons, so this isn't as polarizable. And so in one instant of time, this dipole can't grow that huge because it's got a lot fewer electrons. And so here the dispersion forces are much stronger than there. Does that make sense?
Wait, why does it have less electrons?
Chlorine only has 17 electrons, whereas iodine has 53 electrons.
So the size.
The size, right.
So the higher the molar mass, the higher the boiling point.
Yeah, but I don't like to say molar mass because some people think it's heavy. The heavier the molecule is, the less likely it is to boil away, but it isn't heavy. It isn't the weight of the molecule holding it down. It's the dispersion forces. If we compare butane and acetone, which one do you expect to have a higher boiling point? Well, butane and acetone are around roughly the same molar mass. They're roughly the same molar mass, right? Maybe they are the same. It's because of oxygen. But acetone also has, is that a hydrogen bond? No, this is a dipole. Hydrogen bond, you have to have the hydrogen attached to the oxygen. This is a carbon attached. And so acetone has a dipole interaction in addition to about the same dispersion. And so when we compare molecules, it's the easiest to compare if they're equal in size. If they're unequal in size, you usually give the advantage to dispersion, to the bigger. And so butane has a boiling point minus 0.5 degrees C, whereas acetone 56.2. So significantly higher boiling point. This is a hydrogen bonding interactions. HF has this unusual shape where it forms these kind of clusters due to the hydrogen, maximizing the hydrogen bonding interaction between them. Here you can see water, two waters, hydrogen bonding. Hydrogen bonding is quite strong. If there's hydrogen bonding present, then we normally think that dominates. Here. This gives the open structure to water. You know, ice you want to maximize the hydrogen bonding interaction, so ice is a very open structure, whereas water, liquid water, they're a little bit more random. And so liquid water is actually more dense, you know, it has less empty space than solid water. Sometimes the hydrogen bonding interactions are so strong that dimers are formed. These are two acetic acid molecules, and they're linked together to form a dimer. You've heard of polymers, right? Polymers are a whole bunch of molecules linked together, typically with a bond. But dimers are usually linked together with a intermolecular force here. And so the acetic acid molecules, they don't break free from each other. They are kind of coupled together. And so very high concentrations in the aqueous acetic acid, you get a lot of dimers that form this. Or in the gaseous phase, you know, you get some dimers that form like this. Obviously, the more hydrogen bonding interactions, the better. And so ethyl alcohol, there's just one OH. Ethylene glycol, there's two OHs. And glycerol, there's three. And so glycerol by far is going to have the strongest H bonding interaction of three. If you look at the, we can look at something called the viscosity. You know, ethanol pours like water. Actually, it's a little less viscous than water. But when you get the glycerol pours like syrup. You know, the hydrogen bonding interactions in glycerol are very strong.
Wait, so when it's gone to an oxygen, it's higher? It's stronger?
Yeah. This is we call it intramolecular hydrogen bonding interaction. You know, this hydrogen bonding interaction here is set up within the same molecule. Yeah. And so that's going to keep this position. There usually is free rotation here, but it's kind of stuck here unless the temperature is high. Here's another one. This looks like a dimer, doesn't it? Two molecules that are kind of stuck together by hydrogen bonding interaction. This is between guanine and cytosine and DNA. In fact, DNA, you have the double strands. The double strands are actually dimer. There's just two strands stuck together by a hydrogen bonding interaction. What's that? Oh, the camera. Yeah. We can take a look at this one some more. The dimers, you can see it is there. All right, so let's look at some here. You know, HCl, HBr, HI. You know, as far as dipole moments go, HCl should have the highest boiling point. As far as dispersion forces go, HI. And so dipole versus dispersion, who won? Dispersion. All right, so those are some, so let's take a look at two methanes held together with dispersion only. If you look at this one, this is what, acetone and butane. Acetone and butane are going to be held together by dipole-induced dipole. We don't have to have an instantaneous dipole because this has already got a permanent dipole. This one is lithium ion in pentane. Lithium ion and pentane can attract each other by a charge or ion-induced dipole here, because this thing's positively charged, so it's going to pull the electron density from this molecule to this side and induce a dipole there. Here, water and carbon monoxide are going to attract to each other by a dipole-dipole attraction. All these have dispersion as well. Methanol and water. Methanol and water attract each other by hydrogen bonding. Potassium ions in water, this is an ion dipole attraction. All these are electrical attractions. Here, this is an ion, this is an ion, so we've got an ion-ion attraction. Argons are going to be dispersion only. Here, we can have an ionic bond and a metallic bond. Ionic bonds range from 400 to 4,000. Metallic bonds 100 to 1,000. Covalent bonds 100 to 1,000. So we could see the strength of interactions. You know, these are just the basic ones, but these are mixed here. You can see the strength can range from very high to very low. If you look at this one here, the ion dipole, potassium ions and water. Potassium ions and water are just attracted by an electrical force, you know, the ion plus the dipole of water. But if you look at the strength all the way up to 600 kilojoules per mole, that's like a bomb. Strong. All right, let's continue here with this. Let's look at some properties of liquids quickly. Let me go back to the board here. Properties of liquid, one, boiling point, all right? What can you say? The stronger the IMFs, the higher the boiling point. What is boiling? Boiling is, yeah. And so if you have molecules in the liquid state, the molecules in the liquid state are all held together by what? IMFs. But some of these molecules can escape the surface, because do all these molecules have the same energy? No. Some have enough energy to break free of the surface. The ones that broke free of the surface, we call this, you know, the gaseous molecules. This would be the liquid molecules here. Gaseous state. And the pressure that these generate is the vapor pressure, the gas. So what boiling is it's when the vapor pressure of the gas is equal to the atmospheric pressure. When these two are equal, then we have boiling. And the temperature at which that occurs is the boiling point. And so you have molecules pushing up, atmosphere pushing down. When those are equal, we got boiling occur. And it can occur freely and spontaneously. Whereas when the vapor pressure is high, well, actually, let's make it the opposite. When the atmospheric pressure is high, it contains the And so, let's see. We're going to come back and to talk about this in a moment. But we have boiling point 2. We have heat of vaporization. Heat of vaporization is just delta H of vaporization. This is equal to the heat required to vaporize, usually a mole of liquid. Normally it's in kilojoules per mole. And so the stronger the IMFs, the higher the delta H of vaporization. Water has a fairly high delta H of vaporization. Okay, 3, we have vapor pressure. Let me show a figure on vapor pressure. Here. All right, if we put a liquid into a container like this, some of the liquid molecules will have enough energy to escape the surface. Those are shown in red here. You go into the gaseous phase. This is called evaporation. So we have evaporation occurring, and then we have some molecules in the gaseous phase, which is shown in gray here. But at the same time, some of these molecules in the gaseous phase might come back and strike the surface. If they strike the surface, they could stick due to the intermolecular forces of attraction. And so the ones that come back and stick, it's called condensation. And so normally we have evaporation occur as the concentration or the pressure, the vapor pressure of the gas builds up, the condensation rate increases. Eventually, what will happen is we'll saturate the airspace here with vapor. When we saturate the airspace with vapor, the evaporation rate is equal to the condensation rate. So we have to build up a certain number of molecules. The evaporation rate is going to depend on the temperature. You know, at a higher temperature, the evaporation rate increases, and then we're going to generate more, and therefore we have to generate more until the condensation rate can balance the increased evaporation rate. And so the vapor pressure depends on temperature. The higher the temperature, the greater the vapor pressure. Vapor pressure is the pressure of the gas inside this container. Yeah. So here they're just showing the vapor pressure. Here, the vapor pressure is going to increase with temperature. This is a way to measure the vapor pressure. Let's look at some data. So if we take a look at the vapor pressure, you can see this is for water at various temperatures. So at 25 degrees C, we generate 23.8 millimeters of mercury water vapor or gaseous water. As you increase the temperature, you can see the vapor pressure increases. But there's one temperature you should pay particular attention to, that's 100 degrees C. At 100 degrees C, take a look at what the vapor pressure is. 760 millimeters of mercury. So at 100 degrees C, that's what we call the normal boiling point of water, because at 100 degrees C, the vapor pressure is equal to the normal atmospheric pressure. And so we should have spontaneous vaporization or boiling. Well, anyway, this is the data here showing the vapor pressure. Now, vapor is a gas. And when we plot this out, it doesn't come out linear, you know. Normally, if you go back to the ideal gas law, as the temperature increases, the pressure increases. So if we double the temperature, the pressure should double. But what happens is, as we double the temperature, the pressure increases exponentially. Why is that? Well, the reason that is because there's liquid present. You know, because if we increase the temperature, not only are we going to increase the strength or the energy of the collisions, but we're also going to increase the rate of vaporization, the rate of evaporation. And so what happens is it's nonlinear because as we're increasing the temperature, we're increasing the pressure of the gas, plus we're adding more gas molecules into the vapor state. So when we plot this out, this is, do you know which one of these is water? No. C is water. Do you know how I can tell C is water? Because at 100 degrees C, it's 760. And so B would have a lower boiling point. The boiling point of B would be around 80. The boiling point of A would be, 30s. The boiling point of D is higher, and the boiling point of E is the highest out of all these. The normal boiling point. The pressure can change the boiling point. But when we see it, we see a non-linear dependence. Okay, what are these? E is aniline. Aniline's an organic base. A is diethyl ether. Ether is very volatile. It boils with a very low temperature. B is benzene. C is water. D is toluene. E is aniline. And so this is going by strength of intermolecular force of attraction. And so let's take a look at the vapor pressure in a little bit more detail. And so here we have the vapor pressure versus the temperature. And we see it's going to be curved like this. In Chem 4 and in Chem 1A, what you did was remember linear interpolation? Linear interpolation is you assume that it's fairly linear between these two temperatures. And then you interpolate it. Let's say you had 45, you said it's halfway between the two. Is that totally accurate? No, because it's not linear, it's exponential, it's non-linear. And so when we have one, we know, like for example, water, we know one vapor pressure. Everybody should know this. At 100 degrees C, for water, the vapor pressure is 760 millimeters of Hg. We know that. And so it turns out that there are different equations that fit this, but the easiest equation that we can use is called the Clausius-Clapeyron equation. The Clausius-Clapeyron equation is just a mathematical fit to this, but it's rearranged to make it more useful for us. And we have this, we call it P2 over P1 is equal to delta H of vaporization over R, 1 over T2 minus 1 over T1. I think it's a negative. This is jumping ahead a little bit. Let's see the Clausius-Clapeyron equation here. Is it on the homework? Yeah, it should be.
We know the test.
It might be. Okay. Oops. All right, that didn't work.
Do we have to memorize that equation?
No. You don't have to memorize that equation. Wrapped around. This. Browse this. All right, how do you use the Clausius-Clapeyron equation? How you use the Clausius-Clapeyron equation is for two things. Let's see, where is that? This is the Clausius-Clapeyron equation, 12.2. But basically, this. If you know what delta H of vaporization is, then we could figure out the vapor pressure at any temperature. If we know this and normal boiling point, then can determine P that at any temp. And so let's say we want to know what water would boil at on top or in Denver, let's say. If we want to know what temperature water will boil at in Denver, then we have two choices. Actually, this is a natural law. This is, if you plot vapor pressure, which is exponential, using natural law, you can make a linear function. Linear functions are just easier to fit, but we aren't going to use it. And so you have two choices, three choices. If you want to know what the boiling point of water is in Denver, one, we got to know what the pressure is in Denver. Does anybody know what atmospheric pressure is in Denver? No, we look it up. And so we find the pressure. Let's say the pressure is something like 740 millimeters of mercury. Well, 740, I don't have a data entry point there. So what can I do? I could do a linear interpolation. Is that very accurate? Yeah. I mean, it depends on how close your data is. Two, I can plot this out. I'll plot out all this data and get this black line. I plot out all this data and get this black line, and then I'll go to 740 and then drop down. I'll see how it's around 80-something degrees C. So that's okay, right? But do you want to plot it out? No. This way, if we use the Clausius-Clapeyron equation, we don't have to plot anything out. All I do is I look up delta H of vaporization. It's like 44 kilojoules per mole or something like that. Plug that in here. I know what its normal boiling point is, so I'll call that T1. T1's 100 degrees C converted to Kelvin. And then P2 would be P1 would be 760 millimeters of mercury. And then plug in 740 millimeters of mercury here, and then solve for T2.
And the R value?
R is 8.3145 joules per mole Kelvin. I got to make sure the units cancel out, so I got to go from kilojoules to joules for delta H vaporization. So does it look like the Clausius-Clapeyron equation is the way to go? Do you want to plot it out like this, like a vapor pressure curve? No. Do you want to do linear interpolations in a table like this? No. What you want to do is you want to just plug it into this equation here in your book. The problem with plugging into this version of is this pre-exponential, what we call a pre-exponential. It's the A, where the A term is actually the slope. And so in order to use equation 12.1, we'd have to plot it out, generate the slope, and determine the y-intercept. Do you want to do that? No, not at all. And so this, might not be so useful. The good thing about this is use some more data. And so that's an application. Clausius-Clapeyron, we know delta H vaporization for water is 44.0 kilojoules per mole. We can determine the boiling point at any temperature we want for water, including higher temperatures. So for example, if you had a pressure cooker that went up to 2 atmospheres, can you determine the boiling point of water? Yeah, at 2 atmospheres, you could. Plug in delta H 44. T1, 100, converted to Kelvin. P1, 760. P2 would be double that, 1520. And then you can calculate the temperature.
Shouldn't that be the natural light? You deal with that?
Yeah, sorry. This is, I missed something here. This is the natural log, ln.
No, the
No,
pressures.
people.
Oh, the pressures, sorry, this one. ln of P2 over P1, that's correct. How do you isolate the T? Yeah, you just take E to both sides, and then you can isolate the T. All right, any questions on this? So what was the homework problem that I assigned for this? We can do it really quick.
Is it the end of chapter 12? Is this the end of chapter 12?
Yeah.
Yeah, we're going to finish chapter 13.
Wait, do we have to finish something?
All right, let's do number 41. You want to try that? This is an example, or do you think you guys have this covered? Example? All right. So 41, the normal boiling point, so we're given the normal boiling point of acetone in the forward laboratory industrial solvent is 56.2 degrees C, and its delta H of vaporization is 25.5. At what temperature does acetone have a vapor pressure of 375 millimeters mercury? And so at 375 millimeters mercury, that would be, the boiling point under a vacuum, let's say, or very high altitudes. And so you just plug in the numbers here. It would be ln P2 will 375, P1 760, which is equal to minus delta H 25.5, is that right? Kilojoules per mole, divided by R, 8.3145 joules per mole Kelvin. So kilojoules don't cancel out, so we need to convert it to joules. Just times 1,000 joules, the kilojoule, that would be the easiest. Times 1 over T2 minus 1 over T1. T1 is 56.2 plus 273. Okay, and there we have it. Let's solve for T2.
I didn't know they changed P1, P, or P2.
What's that?
P1 is always going to be P again.
P1 is always what?
Going to be P again.
No.
I didn't know the P1 is 760 is present.
Because they told us the boiling point. The normal boiling point. Normal boiling point means under normal atmospheric pressure. What is normal atmospheric pressure? 760. So you have to have a number. This one is estimate the normal boiling point. And so they give us the vapor pressure of methyl alcohols 40 millimeters mercury at 5 degrees C. Use this value to determine the normal boiling. Well, normal boiling point would have a vapor pressure of 760 millimeters of mercury. All right, so that's vapor pressure. And then we have a couple of other properties. One property is going to be, another property, excuse me, is going to be surface tension. Yeah. Yeah. Surface tension, which would be this. Surface tension is the energy required to increase the surface area of a liquid. What's that?
That's the third one.
What did we do?
What did boiling point, vaporization, vaporization, and then what else?
Delta H and vaporization? Yeah. This would be 4. If we look at a surface molecule versus an interior molecule or bulk molecule, the interior molecules are going to be stabilized by intermolecular attractions all around it in 3 dimensions, whereas a surface molecule is only going to be stabilized by intermolecular attractions going in towards the liquid. And so it turns out that surface molecules have higher energy than interior or bulk molecules. And so in order to increase the surface area of a liquid, you have to go from lower energy to higher energy to create more surface molecules. In other words, you have to break some of these intermolecular forces to bring it up to the surface. And so the stronger the IMF, the higher the surface tension.
Okay, so we're breaking down the IMS to,
Yeah, you're going to be breaking the IMFs. So basically, it's this. If you count this, this is 1, 2, 3, 4. This is 1, 2, 3, 4, 5, 6. Okay? And so we have to eliminate some of those in order to bring this molecule to the surface. And so here, the needle's more dense, obviously, but it won't sink because the gravitational energy is less than the surface tension in this case. It costs more energy to break the surface than to let this drop in terms of gravitational potential. And so that's unexpected behavior there. Here you could just see it. Surface molecules have higher energy than interior molecules. Okay, surface tension is going to be related to these things here. So let's look at wetting and beating. If we have this glass slide over here, this is clean glass. Clean glass, water should wet the surface like this. Whereas dirty or oily glass, water beads the surface like this. And so the difference between wetting and beating is this. We're looking at cohesive versus adhesive forces. Cohesive versus adhesive forces. And so when something wets the surface here, that means the adhesive forces are stronger. than the cohesive forces. And so adhesive forces would be, let's say, water and glass. Glass is very polar. Versus the cohesive forces would be water and water. And so it turns out that the attraction between water and glass is greater than water and water. If they put some wax on the surface of the glass plate, like this over here, then we have the opposite thing occur. And so let's look at a wax surface. Wax consists of hydrocarbons. Hydrocarbons are nonpolar. And so here the water is going to bead the surface. And that is the water, in this case, the adhesive forces are weaker than the cohesive forces.
Resume by cohesive.
And so the water and wax attraction, water and wax would be a dipole-induced dipole attraction. And so water and wax would be weaker than water and water. And so that's beating.
What's meant by cohesive?
Cohesive,
Is there a similar term? Those two are similar?
the adhesive versus cohesive. Cohesive are between like molecules or like objects, cohesion between similar. And so in this case, cohesion is between the same. Whereas adhesive is between unlike or different. So adhesive would be between different objects here. And so cohesion, you're looking at the same thing. And so that's the difference between adhesive and cohesive. There's a common application. We see this all the time. We see this in meniscus. So, an example, meniscus. In the meniscus, here, what we'll see is the water climbs up the sides of the glass. Yes. And so water is trying to maximize its contact with glass. It can't get too high. It would if it could, but it can't get too high because gravity, gravitational potential energy depends on how much mass you have. But you can overcome this a little bit by capillary action. Capillary action is if you have a very, very thin tube. And what happens is, since you aren't pulling up very much water because the capillaries are very tiny, the water can climb quite high in this. Because the mass of water you're pulling up is not much. And so we end up with a situation like this, capillary action. You can see that here. Capillary action, the water level is way up here. And so what is that caused by? Strong adhesive forces. Strong adhesive forces is trying to climb up.
Why is glass so polar?
Glass is so polar because a lot of glasses have ions in there. They're silicon, oxygen with ions mixed in. And so the surface is very polar because of the charged ions in there. This is for water. We see adhesive forces are stronger, but if we go to mercury, a mercury meniscus is the opposite. A mercury meniscus is going to minimize its contact with the glass. And so mercury liquid minimizes contact with glass. Why? Because the cohesive forces in mercury are very strong. Why is it strong? Because it's big. It's got a lot of electrons, and so it could have very strong dispersion forces. In fact, mercury only likes mercury, right? Mercury doesn't really like much else. And so if you look at this figure here, you know what that ball is? It looks like a steel ball, but it's not a steel ball. It's hard to make something like this, but what they did was they made a ball of liquid mercury. That's liquid mercury. If you took a hammer or spatula, you could chop it up into smaller balls. You don't want to touch it with your fingers. But you can see, does mercury like to be in contact with this? This is glass, a glass mirror here. Does it like to be in contact with that? Not at all. In fact, on most surfaces, if you spill mercury on most surfaces, it beads up like this into balls. And so that's a pretty impressive size ball. Yeah. And so you can see it's easily overcoming gravitational. And gravity wants to force it all down to the lowest possible height. But the cohesive forces are quite strong. All right. Last property that we're going to talk about is viscosity. Viscosity is just the resistance to flow.
Is also going to be part of properties?
Yeah, properties of liquids. Right. And so the stronger the IMFs, the higher the viscosity. And so the example here is glycerol. Glycerol is like maple syrup. It has very strong hydrogen bonding interactions. Glycerol is thick and syrupy. If you look at glycerol structure, it makes sense because we have 3 OH groups attached to this, making each molecule capable of forming 3 hydrogen bonds. So it keeps it pretty well stuck together.
Isn't it blood? Viscosity of blood is
Viscosity of blood? Blood, I think, yeah, it's pretty high.
Yeah, because when you get stained, then people can die.
Yeah. There's blood thinners to lower the viscosity of blood.
That goes too high. Creates clots.
It creates clots, exactly. All right, those are the liquids, and let's take a look at some solids. Properties of solids. Properties of solids, we have the melting point and the heat of fusion. The melting point is just the temperature at which it melts. Heat of fusion is the amount of energy it takes to melt. And so here we have some melting points. The stronger the IMS, the higher the melting point, the higher the heat of fusion, how much energy it costs to melt. And so we're out of time, unfortunately. But tomorrow we're going to continue.
Wait, are we doing 13 as well?
Yeah. We're doing some 13.